Good afternoon, everybody. My name is Eric Schreiber, and I would like to thank the Ohio Clinicians for Climate Action for inviting me to give this talk. I'm a diagnostic radiologist, retired from the Cleveland Clinic. My interest in global warming actually began when I was a kid. My dad gave me a book to read, Worlds in Collision by Immanuel Velikovsky, which, based on mythology rather than science, speculated that the planet Venus emerged like a comet from Jupiter only about 35,000 years ago. It passed close to Earth not just once, but twice, creating all sorts of earthly mischief, like the parting of the Red Sea. However, in that book published in 1950, Velikovsky did speculate that we would one day learn that Venus was a very hot planet. It didn't take long. That fact was confirmed shortly after by radio astronomy and confirmed again in 1962 by the Venus Mariner 2 mission. Through a series of knowledge iterations on my part back in the 1960s, I became interested in global warming, not only on Venus, but also here on Earth. I have maintained that interest since then. In 2006, I had the honor of an invitation to travel to Nashville, Tennessee for a long and intense weekend with Al Gore, numerous climate scientists, and public speaking coaches. The purpose of the session was to create public speakers on climate change. Since then, I have given over 100 presentations. Today, I have been asked to give a presentation quite different from my usual, comparing the nature of climate change to the current COVID crisis. So the scope of this talk is limited. It won't be the most important talk you hear during this conference. I learned a lot by creating the talk, though, and I hope it's beneficial to you, the listeners. Okay, so we are going to talk about the parallels between these two very different things. And I would start out just by pointing out that 19 of the 20 hottest years on record have occurred since the year 2000. The exception being 1998, where you see this little mosquito, and we will get back to her momentarily. But I would also point out that the 5 hottest years since reasonably accurate records have been started to be kept in 1880, the 5 hottest years on record have been the last 5 years. The exception, 1998, was a stinking hot year. It was the hottest year on record at the time. And that was not just due to climate change, it was also due to an El Nino event that was totally out of the ordinary and made that the hottest year that was ever on record. And it is not a coincidence then that in 1999, the West Nile virus began to take hold in the Chesapeake Bay region and in the New York City metropolitan area. Now, it was undoubtedly North America had been exposed to the West Nile virus before then. But in 1999, it had been hot enough for it to actually take hold, and then it quickly expanded all the way across the country and into Canada and into Central America. And I would point out that just this past August, we had a temperature record of 130 degrees Fahrenheit, which is possibly the hottest temperature ever recorded on planet Earth. And I would also point out to you that that is the same temperature that we cook meat to get it medium rare. And in fact, if we are left outside in those kinds of conditions, we too will find ourselves cooked to medium rare. Now, if we talk about parallels, well, if you look at the symptoms and signs, the final common pathway for heat exhaustion and heat stroke compared to COVID-19, not surprisingly, there is a lot of commonality there. But the most striking thing in common that I found on several fronts between these two things was exponential growth. And we've been seeing a lot more exponential curves lately as we read the literature about COVID-19. Most of you are certainly familiar with or may even have worked with the products of exponential growth. But I do want to talk about it because it's an important commonality. Now, all natural growth shares a common equation. You can change the constants, you can change the units, but this is the general equation for exponential growth. And while we're all familiar with it, we humans have a bit of trouble sometimes visualizing how vast exponential growth or exponential decay can be. So I wanted to go ahead and just show you this example. And what we're going to be looking at is a distance here. We're going to start with a 10 centimeter distance and take it through 14 orders of magnitude. So here we go. 1 centimeter, 1 millimeter, 1/10 of a millimeter, and then we're down to the microscopic cellular level. And as we keep on going, we're down to chromosomes, DNA, the molecular structures. And as we pass through the molecular structures, we find ourselves actually in the outer shells of atoms. And then we plunge all the way in to the nucleus. We are now subatomic, all the way down to quarks. That's 14 orders of magnitude, 1 femtometer, and then we go back quickly, back up through all these levels again, through these 14 orders of magnitude, and back to 10 centimeters. Well, that is exponential decay. And you can see up in the corner, here's an equation for that curve. We started at the point 0, 10 centimeters at 0 time, at 3 seconds. We were at 1 centimeter, at 6 centimeters, at 6 seconds, we were at 1 millimeter, etc. And then the curve became indistinguishable from the baseline all the way out to 42 seconds and 14 orders of magnitude. If we take a look at that in reverse, starting at 1 femtometer at 0 time, at 3 seconds, we have growth up to 10 femtometers. And if we change the units on the curve at 6 seconds, we're at 100 femtometers. And then I pose the question to you, how far up this graph, how far up the y-axis is the end of this curve at 42 seconds and 10 centimeters? Well, the answer is 2 astronomical units. That is, we have to go up twice the distance from here to the sun to get to the top of this 14 order of magnitude graph. Okay, so let's talk about the virus for a minute. The virus presented itself with exponential growth. Here you can see the curve. Here's the equation for this curve. We've got days on the x-axis, and we have total number of coronavirus cases in the United States on the y-axis. And you can see this is looks like an exponential curve, at least initially. If we switch over to carbon dioxide emissions from fossil fuels, well, we've changed the units from days to years. we've changed the units on the y-axis to billions of tons of emitted carbon dioxide. But we have a recognizable exponential curve. And here are those two curves allowing for differences in units. You can see the similarity, and just to prove that point, you can practically superimpose those two curves. Now, what's the biggest problem with climate change? Well, we know it's carbon dioxide. But I want to show you a graphic example. The problem is how much carbon dioxide we are producing. And this is a pictorial just of New York City. And each one of these 33-foot blue balloons represents a metric ton of carbon dioxide. New York City is producing these at 2 per second, every second, 24 hours a day, 365 days a year. Now, clearly, if carbon dioxide came packaged in blue garbage bags, or if carbon dioxide stank to the high heaven, we would have done something about this a long time ago. But no, it's a colorless, odorless gas. This is what 1 hour of carbon dioxide emissions looks like. This is what 1 day of carbon dioxide emissions look like from New York City alone. Bit of a disposal problem. If you look at 1 year of carbon dioxide emissions just from New York City, it would look like this. And this is 55 tons of carbon dioxide emissions from just New York in just a year. But how about if we consider China, the United States, and the European Union combined? Well, that would be over 300 New York cities, or 20 billion tons of carbon dioxide produced per year. But of course, that's not all. We've got 160 or so other countries. They are also producing an additional 20 billion tons of carbon dioxide per year, for a total of about 40 billion tons of carbon dioxide per year. That comes out to over 110 million tons of carbon dioxide each day. Well, we all know that exponential growth cannot continue indefinitely, and there are no known exceptions to that. I want to show you a different kind of curve. This is from the work of Dr. Hansen and his group, and was published a few years back. This is a nearly normal distribution, and what we're looking at is the distribution of sampling from a geographic area. And the geographic area is land masses in the northern hemisphere, summer temperatures during the day, and this particular curve shows this sampling from 1951 to 1980. Now this is a baseline. I would point out to you that on the x-axis we have temperature, but instead of the usual degrees, the units are standard deviations. And I will remind you that 68% of the sampling falls, by definition, within 1 standard deviation of the mean in a normal distribution. 95% falls within 2 standard deviations, and 99.7% falls within 3 standard deviations of the mean. So above and below 3 standard deviations, 0.3% will fall beyond 3 standard deviations. So let's put a green line here to remind ourselves of where the baseline is, and now we're going to start moving forward through the decades. So here's the next decade, and as we keep on going, you can see a few things. One is that the mean is increasing. The mean temperature of this sampling is increasing with time. But you can also see the curve is getting flatter, it's getting wider, it's getting more chaotic. And whereas we used to have half of 0.3, now 0.15% falling below 3 standard deviations, this is so chaotic that we actually have more than that falling below 0.3%, 3 standard deviations on this curve. But look how much we have above 3 standard deviations. We have what used to be 0.15% of samples, we have 14.5%. Well, this is not a normal, quite a normal distribution, although it resembles one. This is a curve I know you all have seen in recent months, and it's the distribution of deaths from COVID-19 if there is no intervention. There's no mask wearing, there's no social distancing, there's no vaccine. The assumption that's made is that when people get infected, they are removed either by death or by immunity. And what will happen is, as the population that can be infected gets smaller, we already saw that this is approximately exponential growth. What happens is we leave that curve and we reach an inflection point, and it peaks and then it decays. And I'm not going to get into the whole thing about flattening the curve. I just wanted to make the point that there's a similarity here. And I also need to look at a more morbid curve that applies to the virus, and it applies to us as well. This is a semi-log plot that all microbiologists in the group will recognize. This is exponential growth of any organism, say bacteria in a petri dish. And as long as there is adequate carrying capacity, you will see exponential growth of that organism. But as the population crosses the carrying capacity, we get to what's called the plateau phase, because we're running out of nutrients for the bacteria to multiply. And ultimately, as we continue to run out of nutrients and maybe introducing toxicity, we enter the death phase. Unfortunately, such a curve does not just apply to bacteria. It can apply to humans too if we are not careful. Which brings us to the potential catastrophe. We have been crossing many tipping points as we have introduced more and more heat-trapping gases into the atmosphere. And we don't know exactly when we will cross a sufficient number of tipping points to have catastrophic and irreversible changes happening that could result in the demise of our species. But we do know that somewhere around 1.5 to 2 degrees Celsius above pre-industrial average temperature, we get into that severe danger zone where we could get into an irreversible crisis. Well, obviously that's the bad news. But so I do want to talk about the solutions that we have at hand. And when I do that, you will recognize the shape of the curves. Here we have an exponential curve showing what has happened to global wind energy capacity from 1980 to 2018. In terms of solar photovoltaic installations, same thing, exponential growth. And there's a particularly dramatic example of that I'd like to share with you, the Chilean solar energy market. Very dramatic exponential growth. And when we shrink that down, we can actually see the shape of that curve. How about storage capacity? We're going to have storage capacity to make renewable energy successful. Well, this is what's happened from 2011 to 2016, and you can recognize the exponential shape of this curve. The units here are energy in gigawatt hours. We're going from 0 to 3. What if we change the scale of this completely? Here is that part of the curve that we were looking at, and now the top, instead of being 3, is 1,000. And there is no reason to believe that we will not continue to double and redouble every 2 or 3 years our cumulative storage capacity. And this is projecting for the next 20 years. And I contend that we will, in fact, be able to fulfill this kind of growth. There's no reason to believe that we won't. And as a result, you can expect to see exponential growth. We already are seeing exponential growth of the number of electric cars on the road. We're seeing exponential decay of lithium-ion battery prices. And we're seeing decay of the cost of solar panels. Now, let's take a real-life example of this. There are many cases, I'm sure, of people deciding to put a 1,000-watt solar array on the roof of their houses. Well, if you had done that back in 1976, that would have cost about $79,000. If you did it in 2019, the solar panels would have cost about $250. That's what exponential decay can do. So, in closing, I would like to remind everybody that this is not the time to panic. This is the time to act while we still can. Making big changes in the way each of us lives is simply not going to be enough. Changing light bulbs simply will not cut it. We are going to have to act collectively to stop the powerful interests that will do whatever they can to disrupt our efforts. These are extraordinary times. Preventing ourselves from being overrun by climate change may be the most important task in all of human history, and it has fallen upon us to do it. Pandemics? Well, pandemics come and pandemics go. We have seen many throughout history. On the other hand, mass extinctions are forever. We have entered into what is commonly regarded as the 6th mass extinction event. And as we all know, we humans are causing it. Arguably, we are only the 2nd life form in history of our planet that has caused a mass extinction. Now, what was the first? I hear you ask. Cyanobacteria were the first. Cyanobacteria were responsible for the great oxygenation event, which occurred in the sea about 2.5 billion years ago. These organisms stumbled upon photosynthesis and thrived as a result. Their waste product was oxygen, which over hundreds of millions of years poisoned most of the anaerobic bacteria in the sea and transformed life on Earth. This perhaps is the finest example that I know of a sea change. Our current sea change of climate is occurring over decades, not hundreds of millions of years. And we have the real potential of driving ourselves to extinction, or perhaps irrelevance. We need to move fast. I leave it to other speakers at this conference to discuss how we will do that. If we fail, then everything else we have worked for will be destroyed. Those who came before us didn't understand the severity of the problem, and those who come after us will be powerless to do so. But for us, there's still time. In this country, we do not have government by the majority. We have government by those who participate. We all must participate. And I thank you for listening.